Clear, calm weather often begins high above our heads when air starts piling up in the upper atmosphere. That extra air has to go somewhere, so it sinks through the column towards the ground. As more air stacks above the surface, the weight of the atmosphere increases, and we measure that as higher pressure. This is the basic engine of a high-pressure system, also called an anticyclone. The key process is upper-level convergence. Air flows together aloft, then descends. At the surface, that sinking air spreads outward from the center of the high, creating surface divergence. In Australia and the rest of the southern hemisphere, that outward flow is turned anti-clockwise by the Coriolis effect, caused by Earth's rotation. While the wind pattern is important, the vertical motion explains the weather we feel. Sinking air is squeezed by the greater pressure closer to the ground. When air is compressed like this, it warms without needing extra heat from outside. Meteorologists call this adiabatic warming. On average, dry sinking air warms by about 9.8 degrees Celsius for every 1,000 meters it falls. Warmer air can hold more water vapor, so its relative humidity drops. That makes cloud droplets evaporate and stops new clouds growing. This is why strong highs are famous for blue skies, dry air, and light winds near the center, where the isobars are often widely spaced. A sinking layer can also create an inversion, where warmer air sits above cooler air near the ground. That lid blocks rising motion. In winter or overnight, clear skies let heat escape from the surface, so the ground cools quickly. If the lowest air reaches its dew point, dew or radiation fog can form, even while the broader high-pressure system remains dry and stable. Not every high forms in exactly the same way. Thermal highs develop when land cools strongly, especially in winter, making dense air settle near the surface. The Siberian high is a classic example. Dynamic highs form when large-scale winds force air to converge aloft, often within the subtropical ridges or around slow-moving waves in the jet stream. Some highs are part of Earth's global circulation. Near the equator, warm air rises, travels poleward high in the troposphere, then sinks again around 20 to 40 degrees latitude. This creates broad belts of semi-permanent high pressure that steer trade winds, ocean weather, monsoons, and even tropical cyclone tracks. When a high becomes slow or stuck, it can turn from pleasant to hazardous. A blocking high diverts rain-bearing lows around it, so one region can stay dry for days or weeks. In summer, persistent sinking air can trap heat near the surface, building a heat dome. In winter, the same calm, clear pattern can produce sharp frosts, fog, and poor air quality. So a high-pressure system is much more than a sunny symbol on a weather map. It is a deep column of sinking, warming, drying air, with winds spiraling outward around it. Understanding that simple motion helps explain clear skies, chilly mornings, heat waves, drought spells, and why storms sometimes miss us completely.